So for this example, we are going to be determining a population standard deviation. It says the following lists the number of home runs hit each season of their careers by Joe DiMaggio and Mickey Mantle. And of course, we can see here is Joe DiMaggio's career home runs right here. And of course, here is Mickey Mantle's career home runs right here. It then says determine each player's standard deviation for the number of home runs hit each season. And then which player was the more consistent home run hitter throughout his career. Now, the very first thing that we want to do is we want to determine if the data is the data of a population or if it's of a sample. So I'm just going to put down step 1 right here. Now, other than the fact that it says that it's a population up here in the title here, the way to be able to tell if it's a population is it says right here, this is their careers. That's their entire career. So this data represents everything that they did. So if it's an everything or an all, it's got to be a population. As opposed to a sample would be a part of the population. It'll just be a subset. And the reason it's important is because a population and a sample, they're symbolized differently. The symbol to show the standard deviation of a population has this symbol. That's a lowercase Greek letter called sigma. That's the best I can draw it. And eventually we're going to be finding averages for this data. And when we find an average, we have to divide by a total. So for a population, we wind up dividing by n, and n is the population total. If this was a sample, which it's not, but if it was a sample, we would symbolize the standard deviation with the lowercase English letter s. And then the way to tabulate the standard deviation for a sample is we wind up dividing by n minus 1, which is known as a degree of freedom. N is the size of the sample, but then we subtract 1. So if it's a population or a sample, we're going to come up with 2 different standard deviations. So it's important to determine what the data represents. Does it represent a population as a whole, or does it represent a sample, which is a subset of the population? So then the next thing we want to do, this is step 2, is we want to find the average or the mean for each set of data. So for Joe DiMaggio's home runs, his mean was 27.7692, and we know how to find a mean. Just add up all his home runs for each season, divide by how many there are. For Mickey Mantle, he on average hit 29.7778 home runs. And we're going to use 4 decimal places just because we want to be as accurate as we can. You don't have to go much more than 4. You can go less, but I want to be a little bit more accurate, so I'm going to use 4 decimal places. The next thing we want to do, step 3, is find the deviations and then square them. Now, a deviation means how something differs or how much it departs from something else. So if Joe DiMaggio over his entire career hit around 27.7692 home runs on average, you could see the first year of his career, he was above his average. He hit 29. If you look at Mickey Mantle, over his entire career, he hit around 29.7778 home runs on average. But the first year of his career, he only hit 13. He's way below his career average. So the difference between what they did and what they did overall is their deviation. So we're going to do that. We're going to take 29 and we're going to subtract by the average. I'm just doing Joe DiMaggio for right now. And then we want to square this result. So I'm just going to enclose it in parentheses and square it. Now in our calculator, I use a TI-30, a scientific calculator. Your scientific calculator should have a square key. Here's mine right here. Or it should have a caret key. That means you could press that and raise a value to a power. I also have these parentheses here. So I'm going to type this in just as you see it. So I'm going to put in a parenthesis, 29 minus 27.7692, close off the parenthesis, and then square it. Hit equal, and it's approximately 1.5149. Then I go to the next observation. I continue. 46 minus 27.7692, and I square it. Now I like to leave this up on the screen here because it shows what I need to do. You can see it right here. I have to take an observation, minus the mean, and then square it. So it shows what I need to do. So I'm going to put in my parenthesis, 46 minus 27.7692, and then I square it. And I come up with 332.3621. And I would do that for each observation of Joe DiMaggio's home runs, and then I would have to do it for each observation of Mickey Mantle's home runs. So here is a table of the square deviations of each player's home runs. As you can see right here for Joe DiMaggio, we did our 29 minus 27.7692. We squared it and we came out with this value here. And if we were to do that for each one all the way down, we would do the same for Mickey Mantle, do for each observation. Eventually what we would have to do then is step 4, is to find the average. And this is where the division by the population comes in. So I would add all these up and divide by how many there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I would divide this by 13. I would do the same for Mickey Mantle. We would have to add them all up and divide by the size of the population, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and then 18. So I would take this and divide it by 18. So then 1,068.2801, 1,068.2081. We'll divide that by 13. And it comes out to be approximately 82.1699. I do the same for Mickey Mantle, 2,425.1116, and divide that by 18. That comes out to be around 134.7284. Now we know that the deviation can't possibly be this high. The average for DiMaggio is a little over 27, so it can't differ by 82 for each one. Same way with here. And that's because we squared our values as we were calculating them. So step 5, the final step, is to then take the square root. of each one of these. So I take the square root. Here is my square root key right here. So since it's above the key, I have to go second and then square root. And you can see the square root symbol pops in. Then I could type in 82.1699. And that comes out to be 9.0648. I then do the same for Mickey Mantle. I'll go back to my second, hit my square root, 134.7284. That comes out to be around 11.6073. So the standard deviation for Joe DiMaggio's home runs for his career, I'm going to write it as sigma because it's a population. It's approximately equal to 9.0648. And the standard deviation for Mickey Mantle's home runs for his career, again, I'm going to write it as sigma since it's a population. And it's approximately 11.6073. Now the big question here is which player was the more consistent home run hitter throughout his career? So since Joe DiMaggio's standard deviation is smaller, 9.0648, than Mickey Mantle's, 11.6073, that means he didn't deviate as much, he didn't depart, or his didn't differ as much as Mickey Mantle's. So since Joe DiMaggio did not waver as much as Mickey Mantle, then we can conclude that Joe DiMaggio was the more consistent hitter. So we'll say Joe DiMaggio.